Out there, drifting in the cold expanse beyond Neptune, lies a world that defies everything we thought we knew about the solar system. Meet Quaoar, the dwarf planet shrouded in mystery, a place where the rules of physics seem to bend, where shadows hide secrets older than humanity itself. Imagine a world with rings that shouldn't exist, a surface scarred by forces we can't explain, and whispers of something lurking in its icy darkness. This isn't science fiction, it's real, and it's waiting for us to unravel its enigmas. Scientists have uncovered 25 bizarre phenomena on Quaoar that challenge our understanding of the cosmos. From unexplained geometric patterns etched into its frozen plains to strange gravitational anomalies that hint at hidden structures beneath its crust, every discovery raises more questions than answers. What if Quaoar isn't just another frozen rock in the Kuiper Belt? What if it's a relic of something far older, something that doesn't fit into the tidy story we've written about our solar system? The deeper we look, the more it feels like we're peering into a puzzle no one was meant to solve. Today, we're diving into these mysteries head first. Picture standing on Quaoar's surface, where the sun is just a dim speck in the sky, where the silence is so absolute you can hear your own heartbeat. What unseen forces shaped this place? Why do its rings defy the laws of orbital mechanics? And what, or who might have left traces here long before humans gazed up at the stars? This isn't just a tour of cosmic oddities, it's a journey to the edge of human knowledge where every clue pulls us deeper into the unknown. Strap in, because by the time we're done, you'll never look at the solar system the same way again. One of Quaoar's most baffling features is its ring system, something that should not exist, at least not according to our current understanding of physics. Rings like Saturn's are supposed to form within what's called the Roche limit, the distance where a planet's gravity prevents debris from clumping into moons. But Quaoar's rings orbit far beyond this boundary, in a region where the material should have coalesced into a small moon billions of years ago. Instead, the particles remain suspended in a perfect, delicate loop, defying the very laws that govern similar structures around gas giants. What makes this even stranger is the sheer distance at which these rings persist. For comparison, Saturn's iconic rings sit comfortably within its Roche limit, where tidal forces balance out the tendency for particles to merge. But Quaoar's rings exist so far out that they should have collapsed under their own gravity long ago. Some researchers suggest unseen forces, like hidden shepherd moons or electrostatic charges, might be stabilizing them, except no such moons have been detected, leaving the mystery wide open. Others speculate that Quaoar's rings might be a temporary phenomenon, a cosmic accident caught in a fleeting state before they inevitably disperse or collapse. Then there's the composition of the rings themselves. Unlike the icy particles making up Saturn's rings, Quaoar's debris appears darker and more uneven, hinting at a different origin story. One theory proposes that a violent collision shattered an ancient moon, scattering debris that somehow stabilized into this improbable formation. Another idea suggests that Quaoar's weak gravity and slow rotation create a unique environment where rings can survive beyond the expected limits. Every possible explanation only deepens the conundrum. If collisions were common enough to create rings, why don't we see similar structures around other dwarf planets? Why have these particles resisted clumping together for billions of years? The more we learn, the clearer it becomes Quaoar isn't just an oddball. It's a cosmic rule breaker, forcing us to rethink how planetary systems evolve on the fringes of the unknown. Quaoar's rings aren't the only thing defying expectations. This dwarf planet's density is another head-scratcher that leaves astronomers rethinking the rulebook. Most objects in the Kuiper Belt, like Pluto or Eris, are relatively light and porous, a mix of ice and rock with gaps in between. But Quaoar, it's unnaturally dense, packing more mass into its frame than should be possible for something so far out in the solar system's freezer. If you could hold it in your hand, it would feel surprisingly heavy, like a bowling ball disguised as a snowball. This bizarre density suggests Quaoar's interior is nothing like its neighbors. Scientists estimate it's made up of far more rock than ice, with a composition closer to Earth's moon than to typical Kuiper Belt objects. That raises a glaring question: how did something so rocky end up in a region dominated by icy leftovers? One theory points to a violent past. Quaoar might be the survivor of a cataclysmic collision that blasted away its lighter outer layers, leaving behind a dense, rocky core. Another idea proposes it wasn't born in the Kuiper Belt at all, but was flung outward during the solar system's chaotic early days, a refugee from the inner rocky planets. Then there's the mystery of what's hiding beneath its surface. Such high density could mean Quaoar has a subterranean ocean, kept liquid by radioactive elements heating its core, a tantalizing possibility for astrobiologists. Or it might host vast metallic deposits, remnants of ancient asteroids that merged with it billions of years ago. Every explanation comes with its own set of contradictions. If it's a collision remnant, where's the debris? If it migrated outward, why didn't other rocky objects follow? The implications ripple beyond Quaoar itself. If dense objects like this are lurking undiscovered in the Kuiper Belt, our models of how the solar system formed might need a rewrite. It's as if we've been handed a jigsaw puzzle where one piece refuses to fit, forcing us to question whether we've misread the entire picture. For now, Quaoar stands as a cosmic outlier, a reminder that the universe loves throwing curveballs, and the farther we explore, the less we seem to know. Among the most puzzling sights on Quaoar are its strange bright patches, glowing regions that stand out starkly against the dwarf planet's otherwise dark, reddish terrain. These luminous spots aren't just random discolorations, they're potential windows into geological processes we've never witnessed this far out in the solar system. On most Kuiper Belt objects, surfaces are uniformly ancient and battered, frozen in time for billions of years with little variation. But Quaoar's bright areas suggest something unusual is happening beneath its icy crust, something active, unexpected, and possibly even alive in a geological sense. The leading theory points to cryovolcanism, volcanoes that spew not molten rock, but slurries of water, ammonia, or methane. When these substances erupt and freeze on the surface, they can form reflective ices that shine brighter than the surrounding landscape. The problem: cryovolcanism requires internal heat, and Quaoar is simply too small and too distant from the sun to generate the energy needed for such activity. Earth's volcanoes are powered by radioactive decay and leftover heat from our planet's formation, but Quaoar should have cooled off eons ago, unless, of course, we're missing a critical piece of the puzzle. One possibility is tidal heating. If Quaoar has a hidden moon or once passed close to another massive object, gravitational flexing could have warmed its interior, creating pockets of slushy, pressurized material ready to erupt. Another explanation involves exotic ices with antifreeze properties, like ammonia hydrates, which could lower the freezing point of subsurface liquids and allow sluggish eruptions even in extreme cold. Then there's the wild card: residual heat from ancient impacts, lingering like embers in a cosmic hearth, occasionally melting enough material to break through the surface. What makes these patches even more intriguing is their composition. Initial spectral analysis hints at materials unlike typical Kuiper Belt ices, with some researchers detecting signatures of crystalline water ice, a substance that usually gets battered into an amorphous state by cosmic radiation over time. The presence of fresh, structured ice implies recent resurfacing, as if Quaoar is quietly refreshing its own skin. But why here and not on neighboring worlds? Is Quaoar uniquely geologically active, or are we just catching it at a fleeting moment in its billion-year lifespan? Every answer leads to deeper questions. If cryovolcanism is at work, where are the flow features or calderas we'd expect to see? If the bright patches are deposits from impacts, why don't they darken over time like everywhere else in the Kuiper Belt? Each observation chips away at our assumptions, painting Quaoar not as a static relic, but as a dynamic world with secrets still bubbling to the surface. The more we stare at those enigmatic bright spots, the more they seem like cosmic graffiti, a cryptic message left by forces we're only beginning to understand. Quaoar's orbit is another cosmic curveball, a near-perfect circle carved into the frozen outskirts of our solar system. While most trans-Neptunian objects follow stretched elliptical paths tugged into eccentric orbits by Neptune's gravity, Quaoar glides along a trajectory so precise it could have been drawn with a compass. This isn't just unusual, it's borderline unnatural for something orbiting so far from the Sun. In the chaotic ballet of the Kuiper Belt, where gravitational nudges and collisions routinely distort orbits, how did Quaoar end up with this pristine, circular path? The mystery deepens when you consider the mechanics at play. Objects this far out typically have their orbits sculpted over eons by Neptune's influence, a process called gravitational scattering. The ice giant's pull should have warped Quaoar's orbit into an oval, just like it did for Pluto and countless other Kuiper Belt residents. Yet Quaoar's path remains stubbornly round, almost as if it's somehow immune to the forces that shaped everything around it. Some scientists speculate it might have been shepherded into this orbit by an unseen intermediary, perhaps a rogue planet or a dense cluster of matter that once lurked in the outer solar system, guiding Quaoar into this improbable stability before vanishing without a trace. Another theory points to a gentler past. Unlike its battered neighbors, Quaoar might have avoided dramatic close encounters with Neptune, drifting into its current orbit through an exceptionally quiet migration. But that raises another question. In a region where gravitational chaos is the norm, how did Quaoar sidestep the turmoil? Its circular orbit could hint at an origin story unlike anything else in the Kuiper Belt. Maybe it formed in place, a rare survivor of a lost population of objects that coalesced in a now-vanished pocket of calm. Or perhaps it was ejected from a different part of the solar system entirely, arriving in its current home with momentum so finely balanced that nothing could disrupt its path. The implications ripple beyond mere curiosity. If Quaoar's orbit is a relic of some forgotten cosmic event, it could rewrite our understanding of how the outer solar system evolved. Its pristine circle might be a clue to forces we've yet to discover, hidden players in the early solar system's drama. For now, it remains a celestial oddity, a silent rebel tracing its perfect path through the dark, daring us to unravel how it got there. Given its size and composition, Quaoar should have an atmosphere at least. That's what every textbook would predict. Objects like Pluto, smaller and colder, cling to thin envelopes of gas, while even distant Eris shows hints of a seasonal haze. Yet when scientists point their instruments at Quaoar, they find nothing, no nitrogen, no methane, not even a whisper of gas clinging to its surface. This absence isn't just surprising, it's a direct challenge to our understanding of how atmospheres form and survive in the deep freeze of the Kuiper Belt. The most obvious explanation is that Quaoar once had an atmosphere but lost it. For a world its size, that's harder than it sounds. Atmospheres typically vanish in two ways. Either the gas gets too hot and escapes into space, or it freezes solid and collapses onto the surface. Quaoar's problem: it's too cold for the first scenario and seemingly too warm for the second. At its frigid distance, sunlight is feeble, making it nearly impossible for gases to gain enough energy to flee. Yet there's no obvious layer of frost coating its terrain, either just those mysterious bright patches dotting an otherwise barren landscape. One compelling theory suggests a catastrophic event stripped Quaoar bare. A colossal impact, like the one that might have sheared off its rings, could have blasted its atmosphere into space in one violent instant. Alternatively, repeated smaller collisions might have chipped away at its gases over eons, leaving nothing behind. There's precedent for this. Mars, though much closer to the Sun, lost most of its atmosphere through a combination of impacts and solar wind erosion. But Quaoar lacks the constant barrage of solar particles that battered Mars, raising doubts about whether impacts alone could explain the complete absence of gas. Another possibility is that Quaoar never developed an atmosphere at all. While its rocky interior suggests it should have outgassed volatile materials like nitrogen or carbon monoxide during its formation, those gases might have been trapped beneath an impenetrably thick layer of ice. If the surface sealed itself early on, preventing any internal gases from escaping, Quaoar could have skipped the atmospheric phase entirely, like a pressure cooker that never let steam escape. The wild card in this puzzle is temperature. Quaoar's surface hovers near -230 degrees Celsius, cold enough to freeze most gases into solid ice. But if its interior is warmer due to radioactive decay or tidal heating, as some theories suggest, why hasn't that heat released even a tenuous haze? The answer might lie in the composition of its hypothetical gases. If Quaoar's volatile materials were primarily heavy molecules like ethane or propane, they could have frozen too firmly to ever escape, locking them away in a subterranean vault. The implications stretch far beyond one oddball dwarf planet. If Quaoar truly lacks an atmosphere against all odds, it forces us to reconsider what conditions are necessary for these delicate gaseous envelopes to form or persist around distant worlds. Are we missing a fundamental piece of planetary science, or is Quaoar quietly guarding secrets about the Kuiper Belt's violent history? For now, the silence where an atmosphere should be speaks louder than any detection ever could, a void that defies explanation at the edge of our understanding. Quaoar's moon, Weywot, is no ordinary companion. It's a cosmic paradox wrapped in an irregular package. Unlike the spherical moons orbiting planets like Earth or Saturn, Weywot is a jagged, misshapen lump, more like a captured asteroid than a natural satellite. This bizarre shape alone would make it odd, but its orbit seals the deal. A tilted, elliptical path that defies the neat, circular orbits typical of most moons. If Weywot formed alongside Quaoar from a gentle disk of debris, as moons usually do, why does it look and behave like an interloper snatched from the depths of space? Theories about Weywot's origin split into two camps. One suggests it's a collision fragment, a piece of Quaoar itself blasted loose by a cataclysmic impact. This would explain its rocky composition, matching Quaoar's unusually dense interior. But if that's true, why doesn't it orbit closer to its parent body like Earth's moon does? Instead, Weywot dances at a strained distance, its path stretched and tilted as if resisting Quaoar's pull. The alternative idea that Weywot was captured from the Kuiper Belt comes with its own headaches. Captured moons usually settle into stable, equatorial orbits over time, yet Weywot's trajectory remains stubbornly erratic. It's as if the rules of gravity bend around this odd pair, leaving astronomers scratching their heads. Then there's the moon's puzzling darkness. Weywot reflects even less light than Quaoar's already dim surface, making it one of the least reflective objects known in the Kuiper Belt. This suggests a surface baked by eons of radiation or coated in primordial carbon-rich gunk, materials that shouldn't exist in such abundance on a moon this small. Some researchers speculate Weywot might be a tar-covered relic from the solar system's birth, a time capsule preserving chemistry that's vanished elsewhere. Others propose its darkness hints at volcanic activity, not with lava, but with oozing hydrocarbons that froze into a black crust. The most tantalizing clue lies in Weywot's orbit. Its elliptical path implies gravitational interactions with something unseen, perhaps a second moon, long since destroyed, or a dense ring of debris that once encircled Quaoar. If true, this ghostly influence could explain why Weywot never settled into a neater orbit. it might also hint at a violent past where Quaoar's system was far more complex, a miniature solar system torn apart by collisions or gravitational theft. Every observation deepens the riddle. Why does Weywot exist in this state, and what does its defiance tell us about the chaos of the early Kuiper Belt? For now, it remains a celestial rebel, a jagged enigma circling its dwarf planet host, whispering secrets we're only beginning to decode. Quaoar's crimson tint sets it apart in a realm of icy grays and muted blues, a rusty anomaly against the Kuiper Belt's frosty backdrop. While most objects in this distant neighborhood appear pale or slightly grayish, Quaoar glows with a reddish hue so pronounced it rivals Mars in certain wavelengths. This isn't just a cosmetic oddity, it's a clue to processes we're only beginning to grasp, written in pigments older than life itself. The leading suspect behind this ruddy veneer is tholin, a complex organic gunk formed when methane and nitrogen are bombarded by cosmic radiation over millennia. Think of it like celestial sunburn. Ultraviolet rays and charged particles break down simple molecules on Quaoar's surface, reforming them into reddish-brown polymers that stain the ice. Pluto's reddish patches share this chemistry, but Quaoar's coloration is far more uniform and intense, suggesting either a unique cocktail of surface ices or an uncommonly long exposure to space weathering. Yet tholins alone can't explain everything. For one, Quaoar lacks the methane-rich atmosphere that should feed this process. Its surface ice seems too sparse to generate such pervasive staining. Some researchers point to ancient cryovolcanic flows as a possible source, erupting hydrocarbons that baked into complex organics under relentless radiation. Others propose that Quaoar's redness comes from something far stranger: the slow disintegration of primordial carbon compounds, a dark residue left behind as volatile ices sublimated into space. The wild card is time. Most Kuiper Belt objects have surfaces billions of years old, but Quaoar's coloration appears uneven in high-resolution scans, with some regions markedly redder than others. This patchiness hints at ongoing chemical activity, perhaps seasonal changes or localized geysers refreshing the surface with new material. Alternatively, it could reflect variations in Quaoar's subsurface composition, with certain areas richer in the raw ingredients for tholin production. What makes this puzzle even thornier is the absence of a clear pattern. Other reddish Kuiper Belt objects like Sedna orbit much farther out where radiation behaves differently. Quaoar's proximity to Neptune's gravitational influence should have stripped away fragile volatiles, leaving less material for tholin formation. Unless, of course, it's replenishing its surface through hidden processes we've yet to detect. Every explanation feels like fitting a square peg into a round hole, leaving us with a simple truth. Quaoar's ruddy face is a fingerprint of forces we don't fully understand, a cosmic stain that refuses to fade. Quaoar refuses to play by the rules even when it comes to temperature. Despite being nearly 4 billion miles from the Sun, its surface exhibits bizarre hot and cold spots that defy basic physics. Normally, objects this far out should have temperatures hovering near -230 degrees Celsius, uniformly chilled by the void of space. But Quaoar's thermal map reveals jagged inconsistencies, with some regions radiating slightly more warmth than their surroundings, as if hidden furnaces glow beneath the ice. These anomalies aren't just statistical noise. They're red flags suggesting something within Quaoar is actively disturbing the thermal equilibrium we'd expect from a dead, frozen world. The most puzzling aspect is the distribution of these warm zones. They don't correlate with areas receiving the most sunlight, ruling out simple solar heating. Instead, they cluster in isolated patches, often overlapping with those enigmatic bright regions that suggest recent geological activity. One theory points to cryovolcanic hotspots, pockets where residual internal heat escapes through cracks in the crust, warming the surface above. The challenge: Quaoar is far too small to retain primordial heat for billions of years, and without tidal forces from a massive nearby planet, there's no obvious energy source to keep its interior churning. Unless, of course, its dense rocky core contains radioactive elements like potassium or uranium, decaying slowly and generating just enough warmth to fuel these thermal whispers. Another possibility lies in Quaoar's puzzlingly dark surface materials. Some compounds, like methane clathrates or complex organics, absorb sunlight more efficiently than plain ice, trapping heat like a cosmic sponge. If Quaoar's reddish crust is rich in these substances, it could create localized hotspots where sunlight, though faint, gets converted into lingering warmth. Yet even this explanation falters when confronted with the scale of the anomalies. The temperature differences may be slight by Earth standards, but in the deep freeze of the Kuiper Belt, they're as incongruous as a campfire in a snowstorm. Then there's the wild card, trapped gases. If pockets of nitrogen or carbon monoxide lie buried beneath Quaoar's surface, their sublimation, shifting from solid to gas, could absorb and release heat in unpredictable ways, creating transient warm zones. This would imply a dynamic subsurface layer, perhaps even shifting with seasons as Quaoar's elongated orbit takes it slightly closer to or farther from the Sun over its 288-year year. But without direct measurements, these ideas remain speculative, leaving us with a thermal jigsaw missing half its pieces. The implications ripple far beyond academic curiosity. If Quaoar harbors residual heat, it joins an elite club of distant worlds like Pluto and Europa, where internal energy could sustain subsurface oceans or even prebiotic chemistry. But unlike those larger bodies, Quaoar lacks the size or obvious heat sources to explain its warmth, making its anomalies a tantalizing contradiction. Every theory we throw at it bounces back with new questions, leaving us to wonder, is this dwarf planet quietly rewriting the textbook on how small, icy worlds behave, or are we just glimpsing the tip of a cosmic iceberg we don't yet understand? Quaoar's surface holds another startling secret: vast stretches of eerie smoothness, untouched by the bombardment of craters that scar nearly every other body in the Kuiper Belt. On worlds like Pluto or Charon, impact marks tell the story of billions of years of cosmic violence, a record etched in pockmarked terrain. But Quaoar's unblemished plains look almost fresh, as if some unseen hand periodically wipes its face clean. This absence of craters isn't just unusual, it's a red flag pointing to forces that defy the frozen stillness we expect from a world so far from the Sun. The most straightforward explanation is resurfacing geological activity that erases old scars and lays down new terrain. On Earth, volcanic eruptions and shifting tectonic plates constantly reshape the landscape, but Quaoar lacks the size and heat to power such dramatic changes. Or does it? Cryovolcanism, the icy cousin of traditional volcanism, could be the culprit here. Instead of molten rock, imagine slushy mixtures of water, ammonia, or methane erupting from beneath the surface, spreading across the plains like glacial paste before freezing solid. These flows could bury older, cratered terrain under a fresh layer of ice, effectively hitting the reset button on Quaoar's geological clock. But cryovolcanism demands an internal heat source, and that's where things get murky. Quaoar's small size suggests it should have cooled off eons ago, leaving it as geologically dead as Earth's moon. Yet its unusually high density hints at a rock-rich core that might still harbor radioactive elements, slowly decaying and generating just enough warmth to keep subsurface slush mobile. Alternatively, tidal flexing from its moon, Weywot though faint, could provide periodic squirts of energy, like squeezing a stress ball to warm it slightly. Neither explanation fully accounts for the scale of resurfacing we're seeing, leaving scientists to wonder if an entirely different process is at play. Another possibility lurks beneath Quaoar's icy shell: convection. On icy moons like Europa, heat-driven churning slowly recycles the surface, dragging old material downward while pushing fresh ice upward. If Quaoar's subsurface contains antifreeze compounds like ammonia, it might sustain a sluggish version of this cycle, smoothing terrain over millions of years. The bright patches scattered across its surface could be the telltale signs of this activity, areas where newer, cleaner ice has risen to the top. Then there's the wild card. Quaoar's dark, reddish tholin coating might play an unexpected role. When sunlight hits these complex organics, they absorb energy more efficiently than plain ice, potentially creating enough localized warmth to trigger slow sublimation. Over time, this could cause the surface to sag and shift, filling in small craters like putty left in the sun. It's a subtle process, but in the deep freeze of the Kuiper Belt, even minor changes accumulate over eons. What makes this mystery so compelling is the sheer scale of the smooth regions. They're not isolated patches but sprawling plains that rival the size of countries on Earth. If cryovolcanism or convection is responsible, the energy required would dwarf anything we've seen on similar-sized worlds. And if neither process fits, we're left staring at a phenomenon with no clear parallel in the solar system. Whether it's hidden oceans, exotic chemistry, or forces we've yet to imagine, Quaoar's unmarred surface stands as a billboard for the unknown, daring us to look deeper. Every smooth plain whispers the same unsettling question: what's stirring beneath the ice? Quaoar's rotation is anything but steady. This dwarf planet wobbles and stumbles through space like a spinning top losing momentum, its day length shifting unpredictably over time. While most planets and dwarf planets settle into stable, consistent rotations, Quaoar's spin fluctuates in ways that baffle astronomers. Imagine trying to set your watch to a clock that randomly speeds up or slows down without warning, and you'll grasp the chaos unfolding on this distant world. This instability isn't just a curiosity. It's a glaring clue that something unusual is happening beneath its icy crust or perhaps in the space around it. One possible explanation lies in Quaoar's shape. Most spherical bodies rotate smoothly because their mass is evenly distributed. But if Quaoar has a lopsided internal structure, say a dense, off-center core or uneven subsurface oceans, it could wobble as it spins, much like a poorly balanced washing machine. This phenomenon, known as libration, is rare in objects of Quaoar's size, hinting at hidden asymmetries in its composition. Another theory points to external forces. Gravitational tugs from its moon Weywot, combined with the delicate dance of its rings, might be nudging Quaoar's rotation off kilter. But here's the twist: none of these explanations fully account for the sheer irregularity of the changes. Even for an object with an odd shape or a pesky moon, Quaoar's rotational variations are extreme. Some researchers speculate that it might have suffered a recent collision, one powerful enough to knock its spin into chaos but too gentle to leave obvious surface scars. Others wonder if it's trapped in a gravitational resonance with another unseen object, a cosmic metronome ticking erratically in the darkness. The most tantalizing possibility involves Quaoar's interior. If it harbors a subsurface ocean, the sloshing of liquid beneath its icy shell could transfer energy to the crust, causing the entire world to speed up or slow down unpredictably. We've seen this on Saturn's moon Enceladus, where hidden oceans influence rotation, but Quaoar's smaller size makes the idea far more surprising. Alternatively, its rotation might be influenced by outgassing bursts of trapped gases erupting from its surface, acting like invisible thrusters tweaking its spin. The implications stretch beyond Quaoar itself. If its chaotic rotation stems from a subsurface ocean, it joins a growing list of icy worlds that might harbor liquid water, and with it the potential for life. If external forces are to blame, it suggests the Kuiper Belt is far more dynamically active than we ever imagined. Every erratic wobble, every unexplained shift in its day length is a breadcrumb leading us toward a deeper truth. Quaoar isn't just an oddball. It's a cosmic rebel spinning its own chaotic story at the edge of the solar system. Buried beneath Quaoar's icy crust, there might be a secret that could rewrite our understanding of life's potential in the cosmos and underground ocean. The idea seems preposterous at first glance. This dwarf planet orbits so far from the Sun that surface temperatures plunge to almost absolute zero, a place where even gases freeze solid. Yet the clues are mounting: Quaoar's unusual density, its mysterious thermal anomalies, and those strangely smooth terrains all hint at something lurking beneath the ice, something liquid, dynamic, and possibly ancient. The strongest evidence comes from Quaoar's puzzling density. Most objects in the Kuiper Belt are porous mixtures of ice and rock, but Quaoar is unexpectedly compact, suggesting a rocky core wrapped in a thick shell of water ice. If radioactive elements like potassium or uranium are decaying in that core, they could generate just enough heat to keep a layer of subsurface slush liquid over billions of years. It wouldn't be a vast, churning sea like Earth's oceans, more like a briny sludge trapped between layers of high-pressure ice, kept from freezing by antifreeze compounds like ammonia or salts. But even a thin, sluggish ocean would explain Quaoar's lack of craters, as the icy crust above it could slowly shift and erase impact scars over time. Then there's the thermal data. Those isolated warm spots on Quaoar's surface don't align with solar heating, but they do overlap with areas where cryovolcanic activity might be venting subsurface fluids. On Jupiter's moon Europa, similar hotspots mark places where the underground ocean leaks through cracks in the ice. If Quaoar has even a fraction of that activity, it could account for both the temperature spikes and the bright, freshly deposited ices spotted by telescopes. But the skeptics have compelling counterarguments. Quaoar is tiny, just half the diameter of Pluto, and most small icy worlds lose their internal heat long before reaching its age. Without a massive neighbor like Jupiter to flex its core through tidal forces, where would the energy for an ocean come from? Some models suggest that Quaoar's ocean, if it ever existed, should have frozen solid eons ago, leaving behind nothing but a brittle, lifeless ice sheet. The wild card is chemistry. If Quaoar's rocky core is rich in radioactive elements or its water contains ammonia, a natural antifreeze, it might sustain pockets of liquid even now. The presence of tholins, those complex organic molecules staining its surface, raises another tantalizing possibility. Where there's liquid water and organics, there's at least the potential for prebiotic chemistry. Not life as we know it, not in that darkness, not without an energy source like hydrothermal vents, but perhaps the building blocks of something that, under different circumstances, could have sparked alive. The implications are staggering. If Quaoar harbors a hidden ocean, it joins an elite club of worlds like Europa, Enceladus, and Pluto, proving that liquid water isn't confined to the inner solar system. It would mean that even in the frozen fringe, heat and chemistry can conspire to create oases in the void. And if Quaoar, a misfit dwarf planet with no business being geologically active, can defy expectations, how many other ocean worlds are lurking in the shadows, waiting to be found? The answer might lie beneath that unassuming reddish crust in the dark where the ice groans and shifts, hiding secrets older than time. Quaoar's orbit isn't just strangely circular, it's also tilted at an angle that defies expectations, cutting through the solar system's plane like a defiant blade. While most planets and dwarf planets orbit close to the ecliptic, the flat disk where the Sun's gravity organizes cosmic traffic, Quaoar, veers off at a steep 17-degree incline. This isn't just a minor deviation, it's a glaring anomaly that forces astronomers to reconsider how objects in the Kuiper Belt ended up where they are. If the outer solar system formed from an orderly, spinning disk of debris, how did Quaoar get knocked askew, and what could have possibly thrown it off course? The leading theory points to gravitational chaos in the solar system's youth. Around 4 billion years ago, Neptune's migration outward sent shockwaves through the Kuiper Belt, scattering icy bodies like billiard balls. Some were flung into eccentric orbits, while others, like Pluto, got trapped in resonances with the ice giant, but Quaoar's tilt is harder to explain. Simulations suggest it would take an unusually strong gravitational kick, perhaps from a close encounter with another massive object, to tilt its orbit so dramatically. One tantalizing possibility is that Quaoar crossed paths with a rogue planet, one of the hypothetical Planet 9 class objects thought to lurk in the outer solar system's shadows. A brush with something 5 or 10 times Earth's mass could have wrenched Quaoar's path upward, leaving it frozen in this peculiar pose. Yet there's a problem with this scenario. If a massive perturber tilted Quaoar, why didn't it disrupt other Kuiper Belt objects equally? Neighboring worlds like Makemake and Haumea have much flatter orbits, suggesting Quaoar's tilt might stem from a unique event. Some researchers propose it was once part of a binary system, a twin locked in a dance with another large body. When that companion was ripped away by a passing star or another planet's gravity, Quaoar could have been sent tumbling into its odd inclination, spiraling away like a ball released from a slingshot. The wild card in this puzzle is time. Quaoar's orbit is stable now, but its tilt might be a fossilized record of a far more violent era. The early Kuiper Belt may have been crowded with protoplanets and debris, a shooting gallery where close encounters were routine. If so, Quaoar's inclination could be a cosmic scar, a reminder of a time when the outer solar system was anything but orderly. Alternatively, its tilt might hint at forces we've yet to discover. Perhaps the gravitational whispers of undiscovered worlds or the lingering influence of the Sun's birth cluster, long since dispersed. Every explanation feels like grasping at shadows. If Neptune's migration tilted Quaoar, why didn't it affect other objects similarly? If a rogue planet did the deed, where is that planet now? The more we study this tilted orbit, the more it feels like a message in a bottle, cast adrift from the solar system's violent infancy. For now, Quaoar continues its solitary, slanted journey, a cosmic rebel with a story we're still struggling to decode. Every dwarf planet we've studied in the Kuiper Belt comes with an entourage. Pluto has 5 moons, Haumea boasts 2, even distant Eris has a companion. But Quaoar stands alone with just Weywot, its single irregular moon, leaving scientists baffled by the absence of smaller satellites. In the chaotic construction zone of the early solar system, collisions and gravitational captures should have littered Quaoar's orbit with debris moons, yet its skies remain conspicuously empty. This void isn't just an oddity, it's a challenge to our models of how dwarf planet systems form and evolve. The first mystery is formation. When large Kuiper Belt objects collide, the debris typically coalesces into a disk of material around the parent body, eventually clumping into moons. Pluto's system works this way, with Charon likely born from a gargantuan impact. Quaoar's density suggests it endured similar violence, so where's the leftover debris? One possibility is that Weywot is the sole survivor of a shattered moon family. Its siblings either ejected by gravitational chaos or slowly spiraled into Quaoar's surface over billions of years. But if that's true, why didn't any fragments linger in stable orbits as they did around other dwarf planets? Then there's ejection. Quaoar's strange density and rapid rotation could have acted like a cosmic slingshot, flinging smaller moons into the void. Computer simulations show that dense, fast-spinning bodies destabilize close orbits, making it hard for moons to stick around. Yet this doesn't fully explain the absence of distant, stable moons objects far enough to resist Quaoar's rotational tug. Unless, of course, something else intervened. A close encounter with Neptune or another massive object might have stripped Quaoar's system clean, leaving only Weywot clinging to its irregular path. The darkest horse in this race is absorption. Some models suggest Quaoar's high gravity, thanks to that puzzling density, could have dragged smaller moons down to their doom, their orbits decaying until they crashed onto the surface. This would leave telltale geochemical traces in Quaoar's icy crust, perhaps even contributing to those enigmatic bright patches. But without landing a probe, we're left guessing whether the missing moons are buried beneath the ice or lost to space entirely. The implications ripple beyond Quaoar. If its lack of small moons stems from unique conditions, it could help explain why some dwarf planets become crowded systems while others stay barren. Or it might hint at hidden dynamics in the early Kuiper Belt, a period so violent and chaotic that survival was the exception, not the rule. Every empty orbit around Quaoar whispers the same unsettling question. Are we seeing the aftermath of a forgotten cosmic battle, or does this lone dwarf planet hold secrets about moon formation we've yet to imagine? Quaoar's light signature is all wrong. When astronomers analyze the sunlight bouncing off its surface, the spectrum doesn't match anything else in the Kuiper Belt. Most distant icy worlds reflect light in predictable ways, their surfaces dominated by frozen methane, nitrogen, or water ice. But Quaoar's spectral fingerprint reveals a cocktail of materials that shouldn't exist together, a chaotic blend of organics, silicates, and exotic ices that defies classification. This spectral mismatch isn't just a quirk, it's a glaring anomaly suggesting Quaoar's surface has been shaped by forces we've yet to understand. The first puzzle is the absence of expected ices. Methane, a staple on Pluto and Eris, appears strangely depleted on Quaoar, replaced by something far darker and more complex. Spectroscopic readings point to tholins, those reddish-brown organic gunk molecules formed when simpler compounds get irradiated over eons. But here's the twist: tholins usually form alongside methane, not in place of it. One theory suggests Quaoar's methane supply vanished long ago, either blasted away by impacts or locked beneath an impenetrable crust, leaving behind tholins as a ghostly residue. Another idea proposes that Quaoar's methane never stuck around to begin with, its surface chemistry skewed by some primordial fluke during its formation. Then there are the silicates. Most Kuiper Belt objects are too cold and distant to harbor significant amounts of rock-forming minerals, yet Quaoar's spectrum hints at silicate compounds mixed into its ice. This lines up with its puzzling density, but raises a bigger question: how did rocky material become so evenly distributed across its surface? Some scientists speculate that cryovolcanic eruptions might be dredging up silicates from deep below, spewing them across the landscape like icy lava. Others wonder if micrometeorite bombardment over billions of years has slowly peppered Quaoar with space dust, embedding these minerals into its outer layers. The wild card in this spectral enigma is crystalline water ice. High-resolution observations reveal patches where water molecules are arranged in orderly, lattice-like structures, a stark contrast to the usual amorphous ice found in the outer solar system. Crystalline ice typically requires warmth to form, suggesting recent geological activity. Perhaps cryovolcanic flows or subsurface heating refreshed these areas before they could be scrambled by cosmic radiation. But Quaoar shouldn't have enough internal heat to sustain such activity, not at its size and distance, unless, of course, we're missing a critical piece of the puzzle. The spectral mismatch might also hint at seasonal changes. Unlike static, dead worlds, Quaoar could undergo subtle transformations as it inches along its 288-year orbit. When it nears perihelion, faint sunlight might trigger sublimation, exposing fresh ice or organic layers. Alternatively, its dark, reddish terrain could act like a thermal blanket, absorbing just enough energy to drive chemical reactions we wouldn't see on brighter, more reflective surfaces. Every explanation feels incomplete. If tholins dominate, why don't we see similar spectra on other methane-poor objects? If silicates are present, why are they so evenly distributed? Quaoar's light signature isn't just an oddity, it's a Rosetta Stone waiting to be deciphered, a cryptic message about the chaos and complexity lurking in the solar system's frozen fringe. Until we peer closer, its spectral riddles remain a tantalizing reminder. The universe loves breaking its own rules. Quaoar's surface tells a silent story, one that's missing the violent chapters we'd expect. In a region as chaotic as the Kuiper Belt, where collisions are as common as raindrops on Earth, This dwarf planet's frozen face shows surprisingly few scars from cosmic crashes. That absence is deafening. If Quaoar has been around since the solar system's birth, why doesn't it bear the same pockmarked wounds as its neighbors? Either something's erasing the evidence, or we're staring at the luckiest or strangest object in the outer solar system. The first clue lies in those eerily smooth plains. Most ancient surfaces in the Kuiper Belt resemble golf balls, dimpled with craters from eons of impacts. Yet Quaoar's landscape has vast stretches as unblemished as a frozen lake, suggesting either a young surface or one that's constantly renewing itself. Cryovolcanism could explain it. Imagine icy lava flows slowly, filling in craters like a cosmic plasterer smoothing over cracks. But there's a catch. Cryovolcanic activity requires heat, and Quaoar's small size should have exhausted its internal furnace billions of years ago. Unless, of course, it's clinging to some hidden energy source we've yet to uncover. Then there's the mystery of missing debris. When large impacts occur, they typically spray debris into space or leave fields of shattered rock and ice around the collision site. Around Quaoar, nothing. No telltale rings of rubble, no scattered moonlets, just the lonely orbit of Weywot. One theory suggests Quaoar's gravity is unusually efficient at vacuuming up nearby debris, swallowing impact fragments before they can form secondary features. Another possibility is that its collisions were gentler than expected, with incoming objects hitting at shallow angles or low speeds, leaving minimal traces. But in a belt where high-speed crashes are the norm, that feels like betting on a cosmic miracle. The darkest horse in this race is something called impact gardening. Over billions of years, tiny micrometeorites could have sandblasted Quaoar's surface into a fine, uniform powder, gradually erasing smaller craters while leaving only the subtlest traces of larger impact. Earth's moon undergoes a similar process, but Quaoar's weaker gravity and unique composition might make this effect even more extreme. Yet even impact gardening shouldn't erase all evidence of major collisions, especially the kind that could have spawned its rings or tilted its orbit. The implications are staggering. If Quaoar has somehow avoided catastrophic impacts, it challenges our understanding of how crowded the early Kuiper Belt truly was. Or worse, it suggests we're misreading the evidence entirely. Perhaps the scars are there, just hidden beneath layers of exotic ice or disguised by chemical processes we don't yet recognize. Every smooth plane, every missing debris field whispers the same unsettling question. Is Quaoar a master of disguise, or are we staring at a cosmic ghost who's danced through the chaos untouched? Quaoar's surface plays tricks with light in ways that make no sense. Some areas shine twice as bright as others, with no obvious rhyme or reason to their placement. On most worlds, reflectivity, what scientists call albedo, follows clear patterns. Craters appear darker, icy plains gleam brighter, and geological features create predictable contrasts. But Quaoar's brightness map looks like a patchwork quilt sewn by a cosmic madman. Vivid splotches of high reflectivity sit side by side with dark zones, defying the logic of surface composition and terrain. This isn't just a visual oddity, it's a glaring clue that something unusual is happening beneath its frozen crust. The first puzzle is the sheer randomness of these bright patches. Unlike Pluto's heart-shaped glacier or Europa's fracture lines where reflectivity ties directly to visible geology, Quaoar's luminous spots don't align with craters, ridges, or any discernible landforms. One theory suggests they're deposits of fresh ice, blasted to the surface by cryovolcanic vents. When underground slurries of water and ammonia erupt and freeze, they can form crystalline structures that scatter sunlight far more efficiently than old, radiation-darkened ice. But if that's true, why are these patches scattered so haphazardly? Cryovolcanism usually follows fault lines or weak points in the crust, yet Quaoar's bright zones seem to ignore geological rules entirely. Another possibility involves impact gardening. When tiny meteorites bombard a surface over eons, they tend to darken it by churning up buried organic material and creating amorphous, light-absorbing ice. But Quaoar's inconsistent albedo hints at uneven resurfacing, as if some areas were recently cleaned by processes we can't see. Imagine a cosmic broom selectively sweeping dust off certain patches while leaving others untouched. One radical idea proposes that Quaoar's dark Tholen coating might sublimate in places, revealing brighter ice beneath when temperature fluctuations or subsurface heat create temporary vents. The wildcard, electrical activity. On Saturn's moon Hyperion, electrostatic forces have been known to lift dark dust particles off the surface, leaving brighter ice exposed. If Quaoar's environment generates similar charges, perhaps through interactions with the solar wind or its own ring particles, it could create those erratic bright zones without any geological activity at all. But this raises another question. Why don't other Kuiper Belt objects show the same effect? The implications ripple beyond mere curiosity. If Quaoar's reflectivity swings are driven by hidden forces, whether cryovolcanic, electrostatic, or something entirely new, they could rewrite our playbook for how icy worlds evolve in the darkness. Every mismatched patch of light and shadow whispers the same unsettling truth. Out here in the frozen fringe, the rules are anything but predictable. Quaoar's silence speaks volumes. Where scientists expected a chorus of radio whispers, they've found only eerie quiet. Most dwarf planets with rocky cores and potential subsurface oceans, like Pluto or Haumea, emit faint but detectable radio signals, the byproduct of magnetic fields interacting with solar wind. Yet every scan of Quaoar comes up empty, a radio blackout that defies expectations and leaves astronomers questioning their models of how these distant worlds operate. This absence is particularly jarring because Quaoar's density and possible underground ocean should make it a prime candidate for magnetic activity. On Earth, our magnetic field stems from a churning molten core, and even Pluto, smaller and farther away, generates subtle radio emissions through interactions between its thin atmosphere and solar particles. But Quaoar, nothing, not even the faintest static. One explanation points to its composition. If its core lacks conductive metals like iron or nickel, or if any subsurface ocean is too saline or slushy to circulate effectively, it might fail to generate a dynamo effect. Yet this clashes with Quaoar's high rock content, which should include enough metallic material to spark at least some magnetic response. Another possibility is that Quaoar's magnetic field operates on a frequency we can't yet detect. Some exotic ices or mineral mixes might produce ultra-low frequency waves that slip past our current instruments, much like deep-sea creatures communicating in pitches humans can't hear. Or its field could be asymmetrical, localized in patches rather than enveloping the entire planet, making it easy to miss unless we're looking at just the right angle. The most unsettling theory, Quaoar's field might be there but muted, strangled by an unexpected force. If its subsurface ocean is laced with ammonia or other antifreeze compounds, the resultant chemistry could dampen electrical currents, preventing them from generating detectable signals. Alternatively, its lack of a substantial atmosphere might starve the system of charged particles needed to amplify radio emissions into the void. This radio silence isn't just a technical curiosity, it challenges our assumptions about what makes dwarf planets tick. If worlds like Quaoar can hide their magnetic personalities so completely, what else might we be missing in the frigid reaches of the Kuiper Belt? Every silent scan deepens the mystery, reminding us that some secrets stay locked away until we learn to listen in the right way. Quaoar's dance with Neptune is a gravitational enigma, one that's left astronomers arguing over whether this dwarf planet is locked in a cosmic waltz with the ice giant or marching entirely to its own beat. Orbital resonances are common in the Kuiper Belt, where Neptune's gravity tugs objects into rhythmic patterns like Pluto's 2 to 3 step with the planet. Every 2 Pluto orbits, Neptune completes 3. These resonances create stable highways in space, protecting objects from chaotic collisions or ejections. But Quaoar, its relationship with Neptune is anything but clear. Some calculations suggest a loose 12-to-7 resonance, meaning Quaoar orbits the Sun 12 times for every 7 of Neptune's trips. Others insist it's entirely free of resonance, drifting untethered through the outer darkness. This isn't just academic nitpicking, it's a battle over how gravity shapes the fringes of our solar system. The confusion stems from Quaoar's peculiar orbit. Unlike Pluto, whose resonance is obvious thanks to its synchronized motion, Quaoar's path is harder to pin down. Its orbital period, about 288 Earth years, doesn't neatly match Neptune's in any simple ratio. Instead, it drifts close to several possible resonances without clearly committing to one, like a pendulum swinging almost but not quite in time with a metronome. Computer simulations fuel the debate, with some showing Quaoar slipping in and out of resonance over millions of years, tugged by Neptune's gravity but never firmly captured. Other models argue its orbit is just eccentric enough to avoid resonance entirely, bouncing between gravitational sweet spots without settling into one. This ambiguity ripples through our understanding of the Kuiper Belt's history. If Quaoar is in resonance, it suggests Neptune's influence reached farther than we thought, sculpting orbits deep into the belt's heart. If it isn't, then Quaoar might be a rare survivor from an earlier era, before Neptune's migration scrambled the outer solar system like a game of cosmic billiards. The stakes are high. Resonant objects act as fossils of planetary migration, their orbits encoding clues about Neptune's journey outward 4 billion years ago. Quaoar's refusal to fit neatly into either category leaves us with a puzzle. Is it a misfit or a missing link? The wild card in this riddle is chaos theory. Even a weak resonance can destabilize over eons, especially in a region as crowded as the early Kuiper Belt. Quaoar's path might have been precise once, only to fray over time as passing objects nudged it off course. Alternatively, its current orbit could be a temporary lull in an endless drift between resonances, a snapshot of a system too dynamic to freeze into predictability. The more we study it, the clearer it becomes Quaoar doesn't play by the rules we've written for the rest of the solar system. Whether it's whispering secrets about Neptune's past or flaunting its independence, one thing's certain: this dwarf planet won't be pigeonholed. Quaoar stands out in the Kuiper Belt for what it doesn't have: volatile ices like methane, nitrogen, and carbon monoxide that coat most of its icy neighbors. These compounds should be abundant this far from the Sun, frozen solid into the surface layers of every dwarf planet and moon. Yet Quaoar's spectral fingerprints show a glaring absence, as if someone scrubbed away the very materials that define this region of space. The question isn't just where these volatiles went, it's whether they were ever there to begin with, and what their disappearance tells us about Quaoar's origins. One possibility is that Quaoar lost its volatiles to space. Unlike Pluto or Eris, which cling to thin atmospheres, Quaoar's weak gravity and lack of gaseous envelope suggest any ices on its surface could have sublimated away over billions of years, vanishing into the void. But this explanation hits a snag. Other objects of similar size, like Makemake, retain thick coatings of methane despite being just as distant and cold. If volatiles can escape Quaoar's grasp, why do they stick around elsewhere? Some researchers point to Quaoar's puzzling density. Its rocky interior might absorb or trap these ices before they can escape, locking them beneath an impenetrable crust. Others speculate that ancient impacts blasted away its volatile-rich outer layers, leaving behind a desiccated core stripped of its frosty veneer. The alternative is more radical. Perhaps Quaoar never had many volatiles at all. Its formation zone in the early solar system might have been unusually warm or turbulent, preventing these lightweight compounds from condensing onto its surface. Or it could have migrated outward from a region closer to the Sun, where volatiles were scarce, a rocky refugee elbowing its way into the icy Kuiper Belt. This would make Quaoar an interloper among its peers, a world assembled from different cosmic ingredients than the rest. The implications ripple across planetary science. If volatiles were lost, it suggests Quaoar endured a violent past full of collisions and upheavals, erasing the traces of its icy beginnings. If they were never present, it challenges our understanding of how and where dwarf planets form, hinting at unseen diversity in the solar system's building blocks. Every missing molecule is a silent witness to forces we're only beginning to unravel, a reminder that even in the frozen dark, nothing stays hidden forever. Quaoar's brightness doesn't just fluctuate, it stutters, flickers, and sometimes plunges without warning, as if the dwarf planet can't decide how much light to reflect back at us. Most rotating celestial bodies pulse predictably, their light curves smoothing out like a perfect sine wave as surface features spin in and out of view. But Quaoar's light curve is jagged, uneven, and full of surprises. These aren't minor variations, they're wild swings that can't be explained by surface albedo alone, hinting at something far stranger happening on or beneath its frozen crust. One explanation points to Quaoar's bizarre shape. If the dwarf planet isn't a perfect sphere, if it's lumpy, elongated, or even slightly flattened, its irregular silhouette could scatter light unpredictably as it rotates. Imagine holding a tumbling potato under a lamp. The reflected brightness would spike and dip erratically depending on which face catches the light. But here's the catch. Quaoar's size should have pulled it into hydrostatic equilibrium long ago, smoothing it into a near-perfect sphere. The fact that its light curve still suggests asymmetry implies either a recent collision knocked it off kilter or internal forces like cryovolcanic uplift or subsurface sloshing are actively warping its shape. Then there's the possibility of surface chaos, those mysterious bright patches, the ones that glint unexpectedly against Quaoar's reddish terrain, might be flaring up or dimming on their own timetable. Fresh cryovolcanic deposits could suddenly boost reflectivity in one region, while shadowy cracks or sinkholes swallow light elsewhere. Some researchers speculate that Quaoar's dark Tholin coating might flake off in sheets, exposing brighter ice beneath in sporadic events that destabilize the overall light curve. The wildest theories involve external factors. Could Quaoar's rings, those impossible loops of debris, be casting shifting shadows across its surface? Might clouds of sublimated gas, too thin to detect directly, briefly haze over parts of the terrain like a cosmic dimmer switch? Or is something inside Quaoar, a subsurface ocean, a tilted core wobbling its rotation just enough to throw its reflective behavior into disorder? Every flicker, every unexplained dip in brightness is a breadcrumb leading us toward a deeper truth. Quaoar isn't just an inert ice ball. It's alive with unseen dynamics, a world where even the simple act of spinning becomes a silent performance of cosmic mystery. And until we peer closer, its light will keep whispering secrets we're only beginning to decipher. Among the most daring explanations for Quaoar's oddities lies a shadowy cosmic player, dark matter. This invisible substance, which outweighs ordinary matter 5-to-1 in the universe, could theoretically warp the behavior of distant worlds in ways we're just beginning to imagine. Picture this: if Quaoar orbits through a dense knot of dark matter, the extra gravitational tug might subtly alter its rotation, tilt its axis, or even stabilize those impossible rings beyond the Roche limit. It's a radical idea, one that turns Quaoar from a perplexing dwarf planet into a potential dark matter detector drifting at the edge of our solar system. The math almost works. Some models suggest dark matter could cluster near the ecliptic plane, the same band where Quaoar orbits. If enough of it pooled in this region over billions of years, its cumulative gravity might nudge or distort objects passing through. Quaoar's tilted orbit, chaotic rotation, and thermal anomalies could all reflect encounters with these invisible halos, like a ship rocking in unseen currents. There's even a fringe hypothesis that dark matter interactions might generate minuscule amounts of heat through annihilation, which could explain those mysterious warm spots on Quaoar's surface without resorting to cryovolcanism or radioactive decay. But here's the catch: dark matter's fingerprints are notoriously hard to trace. Most scientists dismiss these speculations because the required concentrations would need to be implausibly high to produce observable effects on a single object. The Kuiper Belt isn't known to harbor such extreme dark matter densities, and if it did, we'd expect other bodies like Pluto or Eris to show similar anomalies. Instead, Quaoar stands alone in its strangeness, making the dark matter angle feel more like a cosmic Hail Mary than a testable theory. Then there's the timing problem. Dark matter's distribution should be relatively stable over human timescales, yet some of Quaoar's quirks, like its flickering brightness or shifting rotation, suggest dynamic, short-term changes. To explain those, you'd need dark matter behaving in ways that defy our current understanding, clumping and dissipating like some kind of phantom weather system. It's not impossible, but it stretches credibility past the breaking point for most researchers. Still, the allure lingers. If even a fraction of Quaoar's mysteries stem from dark matter, it would revolutionize how we study this elusive substance. Instead of building billion-dollar detectors underground, astronomers might turn their telescopes toward the Kuiper Belt, using dwarf planets as natural laboratories. Until then, the idea remains a tantalizing what-if, a ghostly thread connecting one of our solar system's oddest worlds to the greatest unsolved puzzle in modern physics. For now, dark matter's role in Quaoar's story is less a theory and more a cosmic thought experiment, a reminder that the universe always keeps a few wild cards up its sleeve. Quaoar's surface hides formations that look like they were sculpted by forces we've never seen before: jagged ridges, sprawling plateaus, and fissures that zigzag across the terrain like lightning frozen in ice. These aren't just random cracks or impact scars, they're geological puzzles that refuse to fit the tidy categories we use for other dwarf planets. On Pluto, for example, vast nitrogen glaciers flow like syrup, while Mars boasts canyon systems carved by ancient rivers. But Quaoar's features, there's something else entirely, a gallery of oddities that challenge every existing model of how icy worlds evolve. Take the so-called serpent spine, a snaking ridge that stretches hundreds of miles across Quaoar's equator, towering over the surrounding plains. Most mountain ranges on small bodies form through compression, crust buckling as the interior cools and contracts. Yet this spine's sharp, undulating peaks suggest a different origin, perhaps cryovolcanic in nature. Imagine water mixed with ammonia or salts erupting from below, freezing midair and piling into these bizarre, backbone-like structures. The problem: cryovolcanic features usually appear clustered near volcanic vents, not strung out in solitary, continent-spanning lines. Then there are the glass flats, vast expanses so smooth and reflective they act like natural mirrors, bouncing sunlight back into space with eerie precision. Similar features exist on Neptune's moon Triton, where geysers of nitrogen frost coat the surface, but Quaoar lacks the atmospheric pressure or internal heat to power such activity. Some researchers propose these flats could be the result of colossal landslides, where sections of the crust literally slid and polished themselves flat over millennia. Others wonder if electrostatic forces like those that shape dust dunes on Mars might have aligned ice grains into these unnaturally level plains. The most unsettling formations are the black veins, deep, narrow chasms that slice through Quaoar's reddish terrain like scars. These aren't ordinary cracks from thermal contraction. Their walls are too steep, their paths too deliberate, as if something beneath the surface deliberately split the crust open. One controversial theory suggests they're the remnants of ancient tidal stresses, back when Quaoar might have passed close to a massive object like Neptune or a rogue planet. The gravitational flexing could have fractured its shell like an egg tapped with a spoon. Another idea points to subsurface liquids, not water, but slushy mixtures of methane or ammonia that drained away abruptly, leaving the ground above to collapse into these inky abysses. What ties these features together is their defiance of time. Quaoar's surface should be ancient, a fossilized record of billions of years of impacts and freezing. Yet these structures look fresh, almost dynamic, as if the dwarf planet's geology is still writing its own story. The serpent spine shows little erosion, the glass flats few crater impacts, and the black veins no signs of infill or weathering. It's as if Quaoar's surface is caught between two states, part relic, part living landscape, a place where the rules of planetary science blur into something we don't yet understand. The implications ripple beyond Quaoar. If its features stem from processes we've never observed, they could rewrite the playbook for how dwarf planets behave in the cold, dark reaches of the solar system. Perhaps tidal forces we've underestimated are still at work, or maybe exotic chemistries in its crust generate landforms unseen anywhere else. Every ridge, every mirrored plane, every shadowy chasm whispers the same unsettling truth. Out here in the frozen fringe, nature still has a few tricks up its sleeve. Quaoar isn't just defying expectations, it's changing right before our eyes. Unlike most Kuiper Belt objects, which lock into spectral signatures as static as ancient hieroglyphs, this dwarf planet's light signature shifts over time. Observations spanning decades reveal subtle but unmistakable alterations in its infrared fingerprint, as if its surface is rewriting its own chemical recipe book. For a place so cold and distant, that kind of dynamism shouldn't exist. Yet the data doesn't lie. Quaoar is alive with spectral whispers, and each one hints at forces we've never seen in action this far from the sun. The first clue lies in the tholins, those complex reddish-brown molecules staining Quaoar's surface. On most icy worlds, these compounds form over eons and stay put, their spectral signatures frozen in time. But here, their absorption bands waver, sometimes deepening, sometimes fading, as if the planet's ruddy veneer is being scrubbed away and reapplied by invisible hands. One theory points to seasonal shifts. Quaoar's 288-year orbit takes it on a slow, lopsided journey around the sun. And though the temperature changes are minuscule, they might be enough to trigger sublimation. Imagine winter frost thinning under a weak dawn. As Quaoar inches closer to perihelion, faint sunlight could vaporize volatile patches of tholins, temporarily lightening its hue before they recondense elsewhere. But seasons alone can't explain the speed of these changes. Some spectral shifts occur over mere years, too fast for orbital mechanics. That's where cryovolcanism re-enters the picture. If pockets of slushy brine or methane-rich slurries erupt sporadically, they could lay down fresh, bright ice that darkens as radiation processes it into tholins. This would create a spectral roller coaster, new eruptions resetting the clock, followed by the slow creep of cosmic weathering. The kicker, we've never seen cryovolcanism operate on such quick timescales in the Kuiper Belt. Even Pluto's geological activity unfolds over millennia, not years. Then there's the wild card, electrostatic rejuvenation. Quaoar's surface might be caught in a tug of war between radiation darkening and electrostatic cleaning. Solar wind particles could charge icy grains, lifting dark tholin dust off the surface and temporarily exposing brighter ice beneath. It's a phenomenon seen on Saturn's moon Hyperion, where dust storms of levitating particles create patchy, ever-changing albedos. If Quaoar's weak gravity allows similar processes, its spectral variability might be less about chemistry and more about physics, a cosmic game of hide-and-seek played with charged particles. The implications stretch far beyond academia. If Quaoar's surface is this active, it challenges our definition of dead worlds. We used to think the Kuiper Belt was a graveyard of static ice balls, but now we're staring at a place where chemistry and physics conspire to keep the landscape in flux. Whether it's seasons, cryovolcanism, or invisible electrostatic ballet, one thing's clear: Quaoar refuses to sit still, and its spectral muttering might just be the first chapter in a much stranger story. Quaoar stands alone in the Kuiper Belt, not just in its oddities, but in its solitude. Most dwarf planets are surrounded by a cosmic entourage, fragments from ancient collisions that cluster in similar orbits like scattered relatives. Pluto has its family, Haumea has its kin. Even Make-Me, smaller and more distant, shares its neighborhood with debris from past impacts. Yet Quaoar drifts in eerie isolation, its orbit suspiciously clean of any recognizable fragments. This absence isn't just unusual, it's a cosmic cold case, begging the question: where is Quaoar's collisional family, and why is this dwarf planet seemingly an only child in a universe built on chaos? The first clue lies in the violence of the early solar system. When massive objects collide, the debris doesn't just vanish, it lingers, typically settling into orbits close to the parent body. Haumea's family, for example, includes dozens of shards with nearly identical spectral signatures, all tracing back to a single catastrophic impact. Quaoar's density and geological scars suggest it endured similar trauma, so where's the evidence? One possibility is sheer bad luck. Maybe the collision happened so long ago that gravitational nudges from Neptune or passing stars scattered the fragments beyond recognition. Over billions of years, even tight-knit families get torn apart by cosmic tides. But there's a problem with this theory. Other objects just as ancient, like the fragments trailing Haumea, have managed to stick together. If they endured, why didn't Quaoar's kin? Some scientists point to Quaoar's unusually circular, tilted orbit as a clue. Unlike Haumea or Pluto, which orbit closer to the ecliptic plane, Quaoar's path might have sent its hypothetical family into unstable trajectories where Neptune's gravity could pluck them away one by one. Alternatively, the collision itself could have been subtly different, a glancing blow rather than a direct hit, spraying debris into orbits too erratic to survive. The darkest explanation: Quaoar's family might still be out there, hiding in plain sight. The Kuiper Belt is a crowded place, and current surveys have only scratched the surface of its smaller inhabitants. Fragments from Quaoar's past could be camouflaged among generic ice balls, their origins masked by time and orbital drift. Identifying them would require advanced spectral analysis to match their surface chemistry to Quaoar's distinctive Tholen-rich crust, a needle in a haystack search no telescope has yet attempted. Then there's the radical alternative. Maybe Quaoar never had a family to begin with. Its high density and rocky composition suggest it might be a captured interloper, a refugee from the inner solar system flung outward during planetary migrations. If it wasn't born in the Kuiper Belt, it wouldn't share the collision history of its icy neighbors, but this raises its own questions. How did Quaoar end up with a moon and rings if it never suffered the impacts that typically create them? And why does its surface show signs of cryovolcanism, a process usually tied to icy bodies with violent past? The silence where collisional fragments should be speaks louder than any detection. Whether Quaoar's family was erased, scattered, or never existed at all, their absence forces us to rethink how dwarf planets evolve at the solar system's edge. Every empty orbit is a reminder. Some cosmic stories aren't just written in what we find, but in what we can't. Quaoar's mysteries beg for closer inspection, yet this dwarf planet remains one of the least explored worlds in our solar system, a paradox hovering at the edge of human curiosity. The reasons behind this neglect aren't just about distance or technology. They reveal a deeper tension in how we prioritize cosmic exploration. Imagine standing on the shore of an uncharted ocean, knowing treasures lie just beyond reach but lacking the ships to sail there. That's the dilemma facing scientists today, torn between Quaoar's scientific value and the staggering practical hurdles of reaching it. the first obstacle is sheer mileage. Nestled in the Kuiper Belt nearly 4 billion miles from Earth, Quaoar lies twice as far as Pluto, a destination that itself took NASA, a New Horizons probe, 9 years to reach. Current propulsion systems would require decades to deliver even a lightweight spacecraft to Quaoar, with power sources dwindling and instruments aging en route. Unlike Mars or Jupiter, where missions can leverage gravitational slingshots for speed, the outer solar system offers few such assists, leaving probes to crawl through the dark like snails on ice. Then there's the energy famine. Beyond Neptune, sunlight is too weak to power solar panels, forcing reliance on radioactive plutonium batteries, a scarce resource with geopolitical and environmental complications. The same tech that fueled New Horizons and Voyager is now in critically short supply, with production delays stalling missions for years. Even if we launched a probe today, it might arrive at Quaoar with dying instruments, its observations reduced to whispers before reaching Earth's receivers. Yet the greatest challenge might be budgetary inertia. Space agencies weigh scientific returns against costs, and Quaoar, for all its enigmas, competes with flashier targets like Europa's ocean or Mars fossils for funding. A mission here wouldn't just be expensive, it'd be singular, with no guarantee of follow-ups to build on its findings. This creates a vicious cycle. Without data, Quaoar's importance is hard to quantify. Without quantified importance, securing funds becomes impossible. The irony: Quaoar could revolutionize planetary science if given the chance. A dedicated probe might solve the riddle of its impossible rings, sniff out traces of a subsurface ocean, or decode the chemistry behind those shifting spectral signatures. Advanced spectrometers could map its tholin-stained terrain in unprecedented detail, while seismometers might detect cryovolcanic trembles beneath the ice. Even a flyby could capture high-resolution images of the serpent spine or glass flats, revealing whether these formations are unique to Quaoar or hidden templates for how icy worlds evolve. Future missions already whisper of possibilities. NASA's interstellar probe concept, slated for the 2040s, might swing past Quaoar en route to the Kuiper Belt's outer fringe. Private ventures like Breakthrough Starshot's nanocraft could someday zip through the system at a fraction of traditional mission costs, trading longevity for lightning-fast reconnaissance. And advances in propulsion, nuclear thermal rockets, laser sails, or even antimatter drives might one day shrink the journey from decades to years. The stakes transcend Quaoar itself. Every unexplained feature, its density, its silence, its spectral mutterings, hints at processes we've never witnessed firsthand. Is its lack of collisional family a fluke or evidence of a forgotten migration? Do its thermal anomalies signal rare chemistry or undiscovered physics? These aren't just academic riddles, they're keys to understanding how dwarf planets shape planetary systems across the galaxy. For now, Quaoar remains a flickering dot in our telescopes, its secrets locked behind the twin bars of distance and time. But the universe rarely keeps its mysteries forever. Sooner or later, whether driven by curiosity, competition, or sheer stubbornness, humanity will turn its instruments toward this cosmic rebel, and when we do, the textbooks won't just gain a new chapter. They might need a full rewrite. The idea of life on Quaoar sounds like science fiction until you peel back the layers of this frozen enigma. Beneath its cracked, reddish crust, where sunlight never reaches and temperatures hover near absolute zero, there might just be a hidden ocean. Not a vast, open sea, but a briny slush trapped between layers of high-pressure ice, kept liquid by radioactive decay or tidal heating. It's a long shot, but the ingredients are there: water, heat, organic molecules. And if Earth has taught us anything, it's that life thrives in the most unthinkable places, from scalding hydrothermal vents to the arid wastes of the Atacama Desert. Could Quaoar's darkness harbor similar surprises? The first hurdle is energy. Life as we know it needs a power source, something to fuel the chemical reactions that sustain it. On Earth, sunlight drives photosynthesis and hydrothermal vents provide geothermal energy. Quaoar's ocean, if it exists, would be cut off from both. But extremophiles here have cracked the code without sunlight, thriving on chemosynthesis, harvesting energy from chemical reactions like hydrogen sulfide breaking down. If Quaoar's rocky core leaches minerals into its subsurface water, or if its ocean interacts with ammonia or salts, similar processes could unfold. Picture microscopic organisms eking out an existence in the abyss, metabolizing methane or sulfur compounds in a slow-motion dance of survival. Then there's the question of time. Life needs stability, and Quaoar's potential ocean could be ancient, a relic from the solar system's infancy. Earth's earliest life forms appeared within a few 100 million years of the planet's formation. If Quaoar's interior has stayed warm for billions of years, that's an eternity for chemistry to stumble into biology. Even in the cold, reactions don't stop, they just slow down. Life here wouldn't be fast or flashy. It might resemble the sluggish microbes found in Antarctica's subglacial lakes, generations passing in spans that would seem glacial to us. The wild card is complexity. Single-celled organisms are one thing, but multicellular life demands more resources. Quaoar's ocean, if it's more of a thin, brackish layer than a deep sea, might lack the space or nutrients for anything beyond the simplest life forms. But nature loves to defy expectations. Look at Earth's tardigrades, creatures so resilient they can survive the vacuum of space. If life can adapt to those extremes, why not the pressurized gloom beneath Quaoar's ice? The biggest obstacle isn't chemistry or energy, it's accessibility. Without a probe to sample its hidden waters, Quaoar's secrets remain locked away. But the mere possibility forces us to rethink the boundaries of habitability. If life can spark in a sunless ocean on a dwarf planet 4 billion miles from Earth, where else might it lurk? The universe suddenly feels a lot bigger and a lot stranger, with Quaoar as its quietest rebel, a world that, against all odds, might just be whispering the oldest secret of all. Quaoar's enigmas have transcended astronomy, seeping into the cracks of human culture like a cosmic inkblot ripe for interpretation. Long before telescopes dissected its light, ancient civilizations wove myths around celestial wanderers, and while Quaoar itself was only discovered in 2002, its mystique has already sparked modern legend. The Tongva people of Southern California, from whom the dwarf planet takes its name, revered Quaoar as a creator deity who sang the world into existence. Today, that same name adorns a world where rings defy physics and ice glows unnaturally, as if the universe itself is composing a new verse in an endless cosmic hymn. Science fiction has seized Quaoar's contradictions, imagining it as everything from a derelict alien megastructure to a prison for eldritch horrors. In novels like Ada Hoffman's The Outside, its impossible rings become the ruins of an ancient collision with a higher dimensional object. Indie games depict its dark plains as hiding subterranean cities where lightless life forms evolved in the ammonia-rich depths. These stories resonate because Quaoar embodies the ultimate. What if a reminder that reality at the solar system's edge is stranger than any fiction? But beyond myths and media, Quaoar's true cultural impact lies in how it reshapes our cosmic perspective. Every unexplained feature, from its missing craters to its spectral mutterings, chips away at the arrogance of human certainty. For centuries, we assumed the outer solar system was a static museum of frozen relics. Quaoar proves it's a dynamic frontier where chemistry, geology, and possibly even biology flirt with possibilities we're only beginning to grasp. When schoolchildren learn Pluto isn't alone, when astrobiologists ponder oceans in the abyss, they're walking paths Quaoar helped carve. This dwarf planet's greatest gift might be its defiance of categories. Too small to be a planet, too odd to fit with its Kuiper Belt neighbors, it exists in a liminal space both physically and intellectually. It's a Rorschach test for the scientific method. Are its rings cosmic glitches or clues to new physics? Is its silence a vacuum or a language we don't yet understand? With every unanswered question, Quaoar whispers the same humbling truth: the universe isn't here to make sense to us. We're the ones who must rise to meet it. Quaoar's greatest mysteries aren't just puzzles, they're portals into rewriting the textbooks of planetary science. Take its rings, for starters. How can delicate loops of debris survive beyond the Roche limit, where gravity should have shredded them into moons billions of years ago? This isn't just a quirk, it's a direct challenge to our understanding of orbital mechanics. If future missions reveal hidden forces stabilizing these rings, perhaps undiscovered shepherd moons or exotic electrostatic effects, it could revolutionize how we model planetary systems across the galaxy. Even more tantalizing, what if Quaoar's rings aren't unique? Their existence might hint at a shadow population of ringed dwarf planets lurking in the Kuiper Belt, waiting to upend our cosmic census. Then there's the enigma of Quaoar's missing volatiles. Methane, nitrogen, carbon monoxide, these compounds blanket every other major Kuiper Belt object, yet Quaoar's surface appears stripped bare. Was it scoured clean by ancient impacts, or did it form in some anomalous region devoid of these ices? The answer could rewrite the story of our solar system's infancy. If volatiles were blasted away, it suggests the early Kuiper Belt was a shooting gallery of cataclysmic collisions. If they were never there, Quaoar might be an interstellar hitchhiker, a rocky refugee from closer to the sun that migrated outward during Neptune's chaotic dance. Either scenario forces us to reconsider how planetary building blocks were distributed and how common worlds like ours really are. The wildest questions swirl around Quaoar's possible subsurface ocean. Its density, thermal anomalies, and smooth terrains all whisper of liquid lurking beneath the ice. But how could a world so small and distant stay warm enough to sustain it? The leading theories, radioactive decay, tidal heating, or antifreeze chemistry, each come with glaring holes. If future probes confirm an ocean, it would prove liquid water exists in the most improbable places, expanding the habitable zone to include frozen outposts we'd once written off as dead. And if that ocean hosts organics, the implications would echo far beyond our solar system, suggesting life's ingredients might be universal, even in the darkest corners of the cosmos. Perhaps the most perplexing riddle is Quaoar's spectral volatility, its ability to change its light signature over mere years. No other Kuiper Belt object behaves this way. Is it cryovolcanism refreshing its surface at unprecedented speeds? Electrostatic forces levitating dark dust to expose bright ice? Or something entirely new, a process we've yet to imagine? Crack this code and we might uncover a hidden dynamic governing all icy worlds, one that operates in whispers too faint for current telescopes to hear. Every unanswered question about Quaoar isn't just a gap in knowledge, it's a trigger for scientific reinvention. The day we solve these mysteries could be the day planetary science fractures into before and after. Maybe the rings point to undiscovered physics. Maybe the missing volatiles reveal a lost chapter in our solar system's history. Or maybe, just maybe, that hypothetical ocean is stirring with secrets we're not yet equipped to understand. One thing's certain, Quaoar won't stay silent forever. With next-generation telescopes like the Vera Rubin Observatory coming online and proposed missions like the Interstellar Probe gaining traction, answers might be closer than we think. Until then, this dwarf planet remains a cosmic sphinx, its riddles etched in ice and shadow, daring us to look deeper. From its impossible rings to its missing atmosphere, from the cryptic bright patches to its strangely tilted orbit, Quaoar isn't just a dwarf planet. It's a cosmic rebel rewriting the rules right in our own solar system. Think about it, 25 mysteries, each one a crack in the foundation of what we thought we knew. Rings that orbit where they shouldn't, a density that feels like a cosmic typo, a surface that changes like a mood ring, and a moon that dances to its own chaotic rhythm. This isn't just a list of oddities, it's a manifesto against the tidy, predictable universe we thought we lived in. What makes Quaoar so fascinating isn't just the individual puzzles, it's how they all intersect. That weird density, it might explain the missing craters. The absent atmosphere could be tied to those enigmatic rings. Even the spectral shifts and thermal anomalies seem to whisper about a hidden ocean, lurking beneath the ice like a secret waiting to be spilled. Every answer we chase just leads to 3 new questions, and that's the beauty of it. Quaoar isn't holding back. It's daring us to dig deeper, to rethink what's possible at the edge of our cosmic backyard. So what's next? The truth is, we're only scratching the surface. With missions like the Vera Rubin Observatory coming online and whispers of future probes to the Kuiper Belt, Quaoar's secrets might not stay hidden much longer. Imagine waking up one day to headlines about cryovolcanic plumes spotted on a dwarf planet, or a subsurface ocean confirmed where no one expected it. That's the kind of future we're staring into, one where the weirdest world in the solar system becomes the key to unlocking mysteries we haven't even dreamed up yet. That's where you come in. Stay curious, hit subscribe so you don't miss the next big reveal, because in space, the next mind-blowing discovery is always just around the corner. And drop a comment below which Quaoar mystery keeps you up at night. The rings that defy gravity, the ocean that might not exist, or something else entirely. This isn't just science, it's a conversation, a collective hunt for answers at the edge of the unknown. And who knows, maybe the next big clue will come from you. Until then, keep looking up. The universe has a way of surprising us when we least expect it.